For decades, China's cities have been flooding faster than engineers could drain them, and the gap between the two has been widening every year. Since the 1980s, rapid urbanization sealed hundreds of thousands of hectares of floodplain under concrete, and each new layer of pavement sent stormwater rushing towards city drains in a tighter, faster pulse. By the early 2000s, more than half of China's large cities were reporting regular urban flooding, and economic losses were rising sharply decade after decade. Engineers responded with what engineers always reach for: bigger pipes, deeper tunnels, more pumping stations. And the floods kept getting worse. So China tried something that, when it was first proposed by landscape architect Kong Jianyu, struck most city planners as either decorative or delusional. Rather than building faster drains, retrofit cities to hold water the way a wetland does. So how did a country that paved its floodplains into oblivion attempt to turn its megacities into sponges? And what happened when reality tested the idea? Before Chinese cities were cities, the land they were built on did something that no drainage engineer has ever fully replicated. Natural floodplains were not flat, dry land that occasionally flooded. They were storage systems, layered with wetlands and shallow ponds that filled gradually during rain, then released water slowly over days and weeks as soil absorbed, plants transpired, and channels carried the overflow at their own unhurried pace. The Yellow River Valley, the Yangtze Basin, and the Pearl River Delta all developed over thousands of years inside landscapes that treated flooding as a controlled rhythm, not a catastrophe to be expelled. Water moved through those landscapes slowly because it had places to go that were not the drain at the end of the street. It soaked into permeable soils that held it for weeks before reaching groundwater. It pooled in natural depressions that stored it through dry spells and released it through evaporation during heat. It filtered through root systems and wetland beds before entering rivers. Urban flooding became catastrophic not when rain intensified, but when that whole web of delays and detours was replaced with a single instruction: get the water out as fast as possible. The replacement happened with stunning speed. Between 1980 and the 2010s, China built more urban infrastructure than any nation in human history, and the tools of that construction were impervious. Wetlands were drained and filled to create developable land. Rivers were straightened, channelized, and walled in concrete to increase flood-carrying capacity and free the banks for roads and buildings. Permeable soils were sealed under roads and plazas designed to shed every drop of rain without absorbing any of it. A concrete plaza in front of a building meant no muddy ground, no flooded entrances. But 10,000 concrete plazas across a watershed meant that every storm sent its full volume into the drainage system at once, instead of spreading it across hours of gradual infiltration. Engineers built faster drains to keep up, which worked until rainfall was heavy enough that even the fastest drains could not keep pace with the surge they had helped create. The uncomfortable truth is that drainage design, as practiced for decades, protected individual parcels by pushing the problem downstream, and did so well enough that no one had to reckon with what was accumulating at the end of the pipe. By the time the reckoning arrived, it arrived loudly. Wuhan, a city of more than 11 million people sitting at the confluence of the Yangtze and Han rivers, built extensive drainage infrastructure throughout the 2000s and the 2010s. In July of 2016, more than half the city flooded anyway. A record weekly rainfall of 560 millimeters overwhelmed every system in place. Water levels in the Yangtze reached their fifth highest point on record. More than 1 million people were affected, and the economic damage exceeded 5 billion yuan. Wuhan was one of the first sponge city pilots. Its experience was not unique. Across China's large cities, flood damage kept climbing even as drainage budgets grew, and the pattern was consistent enough that engineers had to confront an unsettling possibility. The infrastructure they kept building was not failing because it was undersized. It was failing because it was the wrong kind of tool for the problem it was facing. Every fix solved yesterday's storm and failed the next one because the fundamental architecture of how water moved through the city had not changed. When Kong Jian-yu began arguing publicly in the early 2000s that China needed to stop fighting water and start accommodating it, the reaction from most of the infrastructure establishment was dismissal. The proposal was to retrofit urban environments with permeable pavements, sunken parks designed to hold standing water temporarily, constructed wetlands and retention ponds, green roofs, rain gardens, and bioswales, all connected into existing drainage networks to slow runoff, reduce peak flood volume, and release water gradually rather than all at once. Critics called it landscaping dressed up as engineering. Politicians worried that parks designed to flood would look like failures the first time they filled with water. Agencies with mandates to build hard infrastructure had no budget categories for gardens and porous pavement. And underneath all of the institutional resistance was a simpler objection. China's cities were growing, space was valuable, and dedicating urban land to nature-based water management felt like a step backward. If this gamble failed politically, the careers behind it would not recover. If it failed hydraulically, floods would still come and the money would be gone. In 2015 and 2016, China's Ministry of Housing and Urban-Rural Development selected 30 pilot cities and committed central government funding ranging from roughly 400 million to 600 million yuan per city per year for 3 years. Construction began. To most observers, what appeared on the ground looked underwhelming. Sunken plazas with gentle slopes, stretches of road resurfaced with unfamiliar textured paving, parks with shallow depressions and planted edges that engineers described as retention features, green roofs on public buildings. None of it was dramatic. Journalists who visited pilot districts early found it difficult to write a compelling story about what amounted to landscaping changes and road resurfacing. Then, a moderate rainstorm passed through a sponge district in Jinan. A city drainage engineer watching from a monitoring station noticed something he had not seen before. The flow meters in the downstream pipes were barely moving. The water that had fallen on the district was somewhere else, soaking into gravel beds and pooling in depressions, and it was not arriving at the drain all at once. Something had shifted in the physics of how the storm moved through the city. The shift did not convince anyone quickly enough to stop the backlash. In 2021, Zhengzhou flooded catastrophically despite years of sponge city investment, and the headline response was exactly what critics had predicted. The program was called a failure, a waste of public money, a project that had not solved the problem it promised to fix. Media coverage quoted residents who had watched sponge features constructed near their neighborhoods and still found water in their streets. The government acknowledged the damage, the death toll, and the inadequacy of what had been built. And the critics had a point, but not quite the one they thought they were making. Zhengzhou's sponge infrastructure was built in specific pilot districts within a city of 9 million people. The rainfall event that hit it was far beyond what any urban drainage system is designed to manage, dropping a volume of water in a single day that approached the city's entire average annual total, hitting a watershed that had been sealed with concrete over decades. Sponge city features were never designed to handle that. The confusion, which was genuine and expensive, was between what the program promised to do and what people heard it say it would do. What sponge cities actually do is change the relationship between rainfall and flood peaks for the storms that happen most of the time. When rain falls on a permeable surface, a fraction soaks in immediately and the rest moves slowly toward the drain, arriving in a lower and longer pulse rather than a sudden spike. Studies on permeable pavement installations in Chinese pilot cities showed peak flow reductions of between 7 and 43%, depending on storm intensity and installation quality. Sunken parks that hold standing water during a storm function as temporary reservoirs, releasing volume gradually as the storm passes instead of sending it all directly into already stressed pipes. Bioswales slow sheet flow along roads, filter pollutants out of runoff before it reaches waterways, and give water contact time with soil that sealed pavement never allowed. Each feature does something modest on its own. Across a retrofitted district, they reshape the storm from a sharp spike into a curve that the drainage system can manage, and the effect does not stop at flooding. Water infiltrating into soil instead of rushing into pipes recharges groundwater that cities had been depleting faster than rainfall could replenish. In sponge districts studied in Guangzhou, surface temperatures dropped by over 10 degrees Celsius in some cases compared to sealed adjacent areas, and air temperatures followed measurably. The city does not just drain better, it behaves differently in heat and drought as well as in rain. After 5 to 10 years of operation across pilot districts, the patterns in the data became hard to dismiss. In Wuhan, more than 380 sponge projects covering parks, green areas, and urban gardens were associated with measurably reduced waterlogging during moderate and heavy storms in treated districts, along with improved water quality and documented biodiversity increases in areas near retention ponds and constructed wetlands. A study published in early 2026 found that diversifying plant species in rain gardens and bioswales raised plant richness by more than 50% in pilot areas compared to conventional urban green spaces. In Jinan, investment in sponge infrastructure was credited with faster post-storm recovery in retrofitted neighborhoods, compared to adjacent areas still relying entirely on conventional drainage. A broader analysis measuring water ecological resilience across pilot cities showed consistent improvement in treated areas, modest in absolute terms but statistically repeatable across sites and years. The numbers arrived after engineers had already watched water move differently through the city, and the combination of observed behavior and accumulated data made a different argument than either the early optimism or the post-Zhengzhou backlash. None of this resolves the hard limits. Sponge city features are designed around storms that occur frequently, the common rains that account for most annual runoff and most chronic flooding. Against extreme events that are becoming more frequent as the climate changes, no amount of permeable pavement prevents catastrophic damage when rainfall volumes exceed the storage capacity of every feature in the system simultaneously. A city's flood risk is also shaped by river systems, upstream land use, and regional hydrology that sponge infrastructure cannot control from within city limits. Retrofitting existing urban fabric is slower and more expensive than building sponge features into new development, and most of China's urban population lives in districts that were sealed under concrete before the program existed. Maintenance matters enormously. Permeable pavements clog as fine particles fill the voids, and installations under poor maintenance conditions lose more than 60% of their runoff reduction effectiveness compared to well-maintained ones. And the political cycle of funding, attention, and accountability that produced the program's early momentum is not guaranteed to sustain the decades of maintenance and expansion that meaningful results require. What China's Sponge City program actually demonstrates is smaller and more important than its most ambitious claims. It shows that cities can restore, inside their own boundaries, some of the hydrological processes that were erased when floodplains were sealed. Not all of those processes, not enough to stop extreme events, but enough to change how ordinary storms behave in ordinary years, and enough to improve the water quality, temperature, and biodiversity of the urban fabric in ways that compound over time. The program did not make China's cities flood-proof. It started making them slower to fail. And the question that the data leaves sitting quietly in the background is not really about China or about floods. If cities were engineered for a century around the single priority of shedding water as fast as possible, moving it away and out and downstream at every opportunity, what else have we optimized in the wrong direction without yet building up enough damage to notice?